idea is, what if there's an object that was so dense that it had a gravitational field and not even light could escape it? This idea was first presented in 1783 in a letter from John Mitchell to Henry Cavendish. However, because at the time, basically light was thought to be a massless wave, this idea wasn't really taken seriously. Until Einstein came up with, basically proved that yes, light is affected by gravity, and he came up with his theory of general relativity, and there's his field equation or something like the sort. And shortly thereafter, Carl Schwarzschild came up with the Schwarzschild metric, which is the solution to the field equation. And then from this one, you could get the Schwarzschild radius, which is given by below. It's basically a radius of that's for radius characteristic for a given mass. It's also a radius at which, if it is sufficiently dense, the force of gravity from the mass would be so great that nothing would be able to, like no force would be able to stop it from collapsing into a point of infinite density, which is basically a point of singularity. There are 4 black hole solutions to Einstein's field theory, which are the Schwarzschild metric, the Reissner-Nordström metric, the Kerr metric, and the Kerr-Newman metric. The Schwarzschild metric is basically describes the gravitational field for a non-rotating or very, very slowly rotating and non-charged object. And the event horizon for a Schwarzschild black hole is basically the Schwarzschild radius. For the Reissner-Nordström metric, equations, we can see that there are 2 horizons which occur at the radiuses on the second one. One is the event horizon, and the second one is the Cauchy horizon. Cauchy horizon. Okay, Cauchy horizon. And we see that if basically RQ, which is length scale corresponding to the charge, is sufficiently small or smaller than the Schwarzschild radius, then it basically behaves like a Schwarzschild black hole. However, if RQ is equal to, or 2RQ is equal to RS, we see that basically these two become degenerate, and we get what is called an extremal black hole, which is a black hole with the minimal possible mass given that can be compatible with a given charges and angular momentum. Then we have the Kerr and the Kerr-Newman metrics, which were our solutions to Einstein's field theory that are rotating. The Kerr metric is uncharged, and whereas the Kerr-Newman is for a charged rotating object. The singularity for a rotating black hole, instead of being a point singularity, is basically like a flattened sphere or disk thing. And there's 2 points, like with the Reissner-Nordström, where we see singularity, which is one is at the event horizon at the Schwarzschild radius, and the other one is another characteristic of the rotating ones is that there is something known as an ergosphere, which within this ergosphere, mass is trapped, but is not being sucked into the black hole, and is basically drawn in a circular path that matches the hole's rotation. The outer limit of this ergosphere is called the static limit, and it's basically the limit at which, beyond which it cannot be not trapped by the hole's rotation. So if we can't see black holes, and they're called black holes because not even light can escape them, and therefore we cannot directly detect them, how do we know that they're there? Even if we can't see black holes do have characteristics that can be detected. One of these is an accretion disk. An accretion disk is basically as the mass, which, because it has the gravitational field, is being drawn towards the black hole, it collects. And then because the gravitational gradient around a black hole is just so great, you end up with a lot of frictional heating. And then that can release in the emit in the X-ray spectrum, which is pretty hot, and we can detect that. The picture is for if there's a black hole star system, binary system, sucking the mass from the star into the black hole. Also, you can see it in this picture too, but we have polar jets, which are basically jets of matter and energy which are being emitted from the black hole. In terms of polar jets, we surmise that because as the accretion disk is rotating, it generates this tangled charge, magnetic field, and it shoots stuff out. Because normally for a black hole, this corresponds to an electron-positron side, we mostly see ones of the electron's nature, which is why normally we only get polar jets coming out in one direction for black holes. Also, characteristic of black holes is because the accretion disks are spinning so quickly, generally near the escape velocity, when the polar jets are also generally shot out at near light speed and are therefore relativistic. We don't actually know why, but they do. However, one theory is that because Einstein's theory of general relativity predicts that rotating bodies would drive space-time with them, as in the diagram, it's possible that this could be one of the causes for could contribute to relativistic jets. Yeah. So we can also basically tell if a black hole is there because it's still a mass, it has mass, it's gravity. We still see the effects of its gravitational field. So we had a talk in gravitational lensing earlier. So
that's a really good picture.
Yep.
I'd use that one.
Yep. So we can't see it, but we can still bend light around it. So if there's an object there and we know there are effects of gravity, but we can't find an object that's actually doing it, it's probably because there's a black hole. Also, when black holes collide, especially supermassive black holes, we expect that they should release gravitational waves, which are fluctuations in the curvature of space-time that propagates as a wave. So while we can't see this collision necessarily, we should be able to detect it, and the picture is basically the artist's depiction of lighting black holes. This is what LIGO is sort of trying to do, well, among everything else they're doing, which LIGO stands for the Laser Interferometer Gravitational Wave Observatory, and is a joint project that's set up between Caltech and MIT to detect gravitational waves. It's basically a laser interferometer, a very big, long laser interferometer, so it can detect very small disturbances. There's two of them that are located around 3,000 kilometers apart, so they can use triangulation to calculate the source of a gravitational wave from very far away. However, we haven't actually seen anything definitive from them yet. We're working on it. Generally, with a gravitational wave from really far away, far away being about tens of millions of light years away, we expect a distortion in this path of around 10 to the negative 18 meters, which is basically less than 1/1000th diameter of a proton, so that's really, really small. However, I think it was apparently in 2005 they achieved a sensitivity level that could actually detect this, sort of. But for this to actually be useful, it needs to be more sensitive. And which is why they're developing something called advanced LIGO, which will make it more sensitive by around a factor of 10, which should actually be able to unambiguously detect gravitational waves on a regular basis and hopefully catch colliding holes. So, in conclusion, while we've never actually directly detected a black hole, and probably never will, it doesn't mean they're not there, and there's a lot of ways we can see them. We can find them, locate them, surmise that they are present. Yeah, the end.